Okay, everyone, let's get started. So we are now starting our third unit of the course. And this third unit has to do with rates of reaction. So energy transformation takes place in our bodies whenever we eat food and we transform that energy into ATP or cellular energy, the type of energy that then our cells can spend and use. And just in a similar way, machines also convert energy by using chemical fuels and turning them into mechanical energy to do work for us. So in this unit, we'll learn more about energy transformations and the factors that affect their rates of reaction and their kinetics. Our first lesson in this unit is on thermochemistry. Heat transformations, as we talked about, take place every day in both living organisms and in machinery. Cars, for example, convert gas, which is a form of chemical energy, into mechanical energy to propel the car forward. Heat is also lost in this process. And in living organisms, it is cellular respiration that converts simple sugars, which is our chemical energy, into cellular energy, heat, carbon dioxide, and water. And heat is lost in the process. So the study of this heat transformation is called thermochemistry, and it is the focus of our lesson today. To begin with, let's cover some definitions and some thermodynamic terms so we understand what each of these terms mean. There's a set of terms that are necessary in order to understand what we are discussing when we're talking about thermodynamics. The first one is thermal energy. Thermal energy is the energy available from a substance as a result of the motion of its molecules. For example, when we burn food, we break down sugars into carbon dioxide, water, ATP, and thermal energy, which is heat. The standard international unit, or the SI unit, for measuring the SI unit for measuring work and all forms of energy is the joule, and its symbol is the J. When we talk about chemical system is the set of reactants and products undergoing energy transformations. Chemical systems can be open or closed. Open means that energy and matter can move in or out, or they're closed, meaning that only energy moves in or out. There's no matter leaving the system or entering the system. Or they are isolated, which means neither energy nor matter move in or out. So that's the chemical system. Now, what we term as the surroundings is all the matter around the system that is capable of absorbing or releasing thermal energy. So, for example, we can consider the reaction for cellular respiration that takes place in our cells in our body, where sugar and oxygen are transformed into water and carbon dioxide and energy. So in this example, the molecules of the glucose, the oxygen, the water, and the carbon dioxide are referred to as the chemical system, while the surrounding, the extracellular fluid of our cells is the surrounding. Another term is heat. Heat, the amount of heat energy that is transferred between substances, systems, or surroundings. When a reaction occurs, heat is transferred between substances, systems, and surroundings. Two other very important terms are exothermic and endothermic. So exothermic refers to a chemical system that releases energy out into its surroundings. Exo is as a term means out. Whenever you see something that has exo in front, it means out. So exothermic means it releases energy, it puts out energy. And then endothermic is a chemical system that absorbs energy from its surroundings. Endo means in, so it brings in energy, it absorbs energy in from its surroundings. So these two terms are also very important. And then finally, temperature. Temperature is a very familiar term, but in thermodynamics, it's a measure of the average kinetic energy of the particles in a sample. That refers, that's the temperature. So energy is typically defined as the capacity to do work or transfer heat. And for this, we need to understand the concept of work and heat. Work is the energy used to cause an object to move against the force. That's the definition of work. While heat is the energy used to cause the temperature of an object to increase. And thermochemistry is the study of the energy changes involved in chemical reactions. And these changes can be physical, they can be chemical, they can be nuclear. Physical is things like ice melting. That's a physical change. Chemical, for example, rusting of iron. When iron oxidizes, there's a chemical change taking place. Or it can be nuclear, for example, nuclear fission, the type of reactions that happen in the sun. All energy transformations, though, are governed by the first law of thermodynamics. First law of thermodynamics, or it's also called the law of conservation of energy, which states that the total energy of the universe is constant. So in order to talk a little bit more about this, we can look at an example and talk about the concept of the chemical system and the surroundings. We can talk about the combustion of propane in a barbecue. For example, you are barbecuing, you've got your barbecue hooked up to a gas tank full of propane, and here you're converting chemical energy, which is your propane, your fuel, to thermal energy and light energy. So by burning that propane, what you're getting is, you're getting heat. You're getting thermal energy, and that's what will cook your food. You're getting heat, and you're getting light energy. You see the flames on your barbecue. However, the total amount of energy before and after this combustion reaction that you burned this propane remains constant. And we can summarize these ideas in the law of conservation of energy. Remember, the law of conservation of energy says that energy cannot be created or destroyed. Energy is always conserved. We cannot create new energy, nor can we destroy energy by using it up. Energy can only be converted, only be changed from one form into another. In this case, we are changing it from the form of chemical energy to the form of thermal energy and light energy. But the total amount of energy is still the same. Whatever amount of thermal energy we had here as chemical energy will become the same total amount in thermal energy and light energy, because energy cannot be created or destroyed. It can only be converted. So to help us analyze energy conversions in chemical reactions, it's useful to conceptualize the universe in two parts. And the two parts we touched upon when we were talking about our thermodynamic terms. The two parts are the chemical system, and the second part is the surroundings. So it's useful to really break it up into two separate things, the chemical system and the surroundings. So the chemical system is is the reactants and the products that we are studying. And the surroundings is all the matter that is not part of the system. So for example, let's get back to our propane gas barbecue example. So in this example, what's our chemical system? Our chemical system is the reactants and the products. The reactants are things like the propane gas and the oxygen. So these are the things that are being, the reactants that are being used up in this reaction. And the products are carbon dioxide gas and water vapor. That's the product of this combustion reaction. We use propane gas and oxygen, and we convert them through the combustion reaction into carbon dioxide gas and water vapor. So these are these reactants and products are referred to as the chemical system in this example of the propane gas barbecue. Now, what is the surroundings? The surroundings is things like the barbecue, or the food on the grill, or the grill of the barbecue. So that's the surroundings. These are the things that are not the chemical system. So then we have to define whether our chemical system is open or closed. An open system is one that can exchange both energy and matter with its surroundings, whereas a closed system can exchange energy only, and it cannot exchange any matter with its surroundings. It can only exchange energy. So operating a propane barbecue in this example is an open system, because propane gas flows into the burner and thermal energy and the products of the combustion flow out. A chemical reaction that produces a gas in a solution in an unsealed beaker, another example, is also an open system, because energy and matter can flow into or out of that system to the surrounding. And the surrounding for the beaker that's holding a chemical reaction, the surrounding would be the beaker, would be the air around the beaker, for example. Now, so our propane barbecue gas example is an example of an open system, because both energy and matter can flow out and conversely flow in. Now, what can we think of as an example for a closed system? A system where only energy leaves, matter does not leave. For example, I don't know if you guys have seen those glow sticks, the ones that are sealed, and then you kind of give them a little crack, give them a little shake, and it kind of glows in the dark. So those glow sticks are an example of a closed system. Let me know if somebody is not familiar with what am I talking about glow sticks. But anyway, if you are familiar with it, that glow stick is an example of a closed system. So the chemical reaction takes place, no chemical is able to leave that closed plastic seal that's around that glow stick, but what does leave, what is released, is light energy. The stick starts to glow when the chemicals inside start to react and mix together. But the matter or the chemicals remain sealed inside. Okay.
Sorry, is this like an example of like if the glow sticks are a different color, then it's a different type of atom inside of it?
Well, I think I'm not exactly familiar with the specifics of the glow sticks, but I think that, yeah, a different mixture of molecules inside the glow sticks probably are causing a different color of light to emit, to glow out. So that's a very good
I heard
question.
about that somewhere. It was like the gases on the rightmost side of the periodic table that like had different types of lights, like different colors emitted.
Yeah, that's very interesting. I don't know, I have to admit, I don't know the exact chemical reactions that take place in glow sticks, but yeah, glow sticks do come in like some different colors. There's yellows and oranges and pinks and greens. So yeah, I think there are a different set of molecules reacting to produce that different spectrum of light. So yeah, so but in this case, again, what's important to know is that that glow stick is a good example of a closed system, of the chemical energy being converted into light energy, but no chemicals are able to leave the system. The chemicals are sealed inside. What does leave the system is the light that is emitted to the outside. But the chemicals are sealed. So that is an example of a closed system. Any other questions about that idea of the chemical system, the surrounding, open systems versus closed systems? Everybody kind of was able to follow along with that example? Okay, let me know if there's any questions or any comments that come up as we're going through this lesson here. So now the units of energy that are associated with thermodynamics. Traditionally, energy changes in chemical reactions have been expressed in calories. That was the old way, which was a non-SI unit. It's a non-standard international unit, but it's still widely used in chemistry and in biology and biochemistry. And a calorie, which is written as lowercase cal, was originally defined as the amount of energy required to raise the temperature of 1 gram of water by 1 degree Celsius. So that is what was defined as a calorie, is the amount of energy you have to put in to change the temperature of 1 gram of water by 1 degree Celsius. For example, if the water is at 14.5 degrees Celsius, you're going to raise it to 15.5 degrees Celsius. That takes 1 calorie of energy. 1 gram of water by 1 degree is 1 calorie of energy. A calorie now is defined in terms of joule, and joule is standard international unit for energy. And joule, pronounced just joule, and the symbol for joule is J. Many of you may be familiar with this from your physics courses. Was named in the honor of a scientist, a British scientist named James Joule, who did a lot of experiments and a lot of investigation into work and heat. And 1 joule is defined as 1 Newton meter. And it's the energy involved when a force of 1 Newton acts through a distance of 1 meter. That is 1 joule. And 1 calorie, so these are just some relationships I want you guys to be aware of. 1 calorie is equal to 4.18 joules exactly. Okay, that's how much 1 calorie is. Nowadays, 1 calorie is defined in terms of joules, and 1 joule is 1 Newton meter. And so yeah, this is just a little note to remind you what is 1 Newton and what is that kinetic energy. The units of it is 1 joule. But because a joule is not a very large amount of energy, you will often see kilojoules used when we're discussing energies associated with chemical reactions. Okay, so kilojoules, 1 kilojoule is obviously 1,000 joules. And another related energy unit that is used in nutrition, now when you're looking at the back of your food and your drink or your chocolate bar or your candy or whatever is the nutritional value, that calorie, which is written with a capital C, so uppercase C cal versus lowercase c cal. Where is it? I think it was on another slide, but lowercase cal versus uppercase cal. So 1 uppercase cal, this kind of a cal, which is the nutritional calorie, is equal to 1,000 calories or 1 kilocalorie. This gets a little bit hairy and confusing, but just be aware that when you're looking at nutritional calories, every one of those calories refers to 1,000 calories or 1 kilocal, and 1 calorie is 4.18 joules of energy exactly. So where do we get these values? So how do we know, like, how many calories, how many joules, how many units? How can we measure these energy changes that are involved in these chemical reactions? How do we know what they are? Well, before we get to that, there's a few support questions for you guys to test your understandings of the material so far. I really urge you to try and answer all of these. It'll really help you out. So calorimetry is the answer. Calorimetry is the experimental technique we use to measure heat energy changes in a chemical system. And an instrument called a calorimeter is used to measure the heat of a reaction. In a calorimeter, the total amount of thermal energy absorbed or released by a chemical system is given the symbol Q. Okay, so we refer to Q as the total amount of energy absorbed or released by a chemical system in calorimetry. And any heat changes that take place are measured through changes in temperature, whether it be an increase of temperature or a decrease of temperature of the surroundings, which in most cases is the water that is in the calorimetry vessel, or sometimes in the classroom setting, we use a very simple calorimetric setup, and that would be like the water that is put in 2 styrofoam cups here. So here, yeah, I've got, I'm showing you 2 setups. This is like a commercial solution calorimeter that would be used in a laboratory to measure the total amount of thermal energy absorbed or released by a chemical system. And this would be a simple calorimeter that you can also do in a classroom setting by using 2 styrofoam cups, a stirrer, a thermometer, and a styrofoam cover, just to keep as much of the system sealed as possible. But what is important to note is that we can't just simply measure the change in temperature. There's other factors that will depend on the amount of energy transfer. And that is one, the mass of the water, so how much water it is that we have in here. And number 2, the specific heat capacity. Okay. Now, before we get on to our next slide and talk a little bit more about specific heat capacity, I have a little YouTube video that maybe we can watch together. And the link is here. And if you need to go back and watch it again some more, it's an informative one. We can watch it together. Okay. So this is a crash course in calorimetry.
Remember that measuring heat change is closely related to enthalpy, which we defined as the internal energy of a system plus the energy that it uses to push the surroundings back and make room for its own pressure and volume. And at a constant pressure like we have here at the surface of the Earth, that works out to be exactly the same as the heat that's absorbed or released by a reaction. Naturally.
Okay, so that was that Q value that I was talking to you about.
it can be very useful to know how much heat a chemical reaction absorbs or releases. In addition to the exothermic hand warmers that we looked at, there are also endothermic chemical ice packs for treating injuries. The ability to calculate change in enthalpy is also what tells pilots how far the fuel in an airplane's tank will allow it to fly, which I am personally very interested in making sure they get right. One of the ways we can calculate the change in enthalpy of a system is with Hess's law, which you'll recall states that the total enthalpy change for a chemical reaction doesn't depend on what pathway it takes, but only on its initial and final states. It's often expressed in terms of standard enthalpies of formation. That is the amount of heat lost or gained when 1 mole of a compound is formed from its elements. That's how we figured out exactly how much heat my hand warmers release. But that's not the only way that Hess's law can be used. The law itself says nothing about standard enthalpies of formation. Any way that we can figure out the change in heat between the products and the reactants will work just as well. And that's where calorimetry comes in. Calorimetry is the science of measuring the change in heat associated with a chemical reaction. And this may look like a plastic bottle inside of a koozie, but it's actually a calorimeter. A calorimeter can be fancy and expensive piece of hardware, or it can be simple. But no matter what it looks like, it's basically just an insulated container that contains a thermometer, and it can be made out of stainless steel or styrofoam cups, but there really are no fundamental differences in how they work. And you know the general setup by now. The chemicals in the calorimeter make up the thermodynamic system, and everything else is the surroundings. The insulation minimizes the amount of heat that leaks in or out of the system so that we can be fairly confident that any heat transfer is part of the system, not the surroundings. The thermometer tracks the temperature change, which is part of the calculation we have to do. And there's usually some way to stir the solution to make sure that the reaction occurs fully. All right, everybody, safety first, though I really should be wearing gloves. I'm going to put 100 milliliters, also 100 grams, of HCl's 1 molar HCl solution into my calorimeter here. I'll wash the buck. And now I'm going to put the same amount of sodium hydroxide solution. Before I do the reaction, I have to know our starting temperature, so I'm going to stick my thermometer in there and wait for a second to see what it does. It should be roughly room temperature. It's been in the room for a long time. So we are currently at like 20.8 degrees Celsius. So that's like 294 Kelvin. And now I shall add my 100 milliliters of sodium hydroxide. The temperature, unsurprisingly, is rising very rapidly, and I'm doing something right now that you should never ever do, which is stir with thermometer, because if this happens in schools across the world, then there will be a million billion broken thermometers, and the stuff inside these thermometers is not good. So never do what I'm doing. All right, the temperature should be stable. By now we have 28.2 degrees Celsius. Now there's a simple formula that allows us to calculate the heat change of a reaction simply by measuring the change in temperature that occurs in a calorimeter. It says that the change in heat equals the specific heat capacity of the substance times its total mass times the change in temperature. Let's examine the parts of this. First of all, the heat change in the calorimeter formula is normally represented by a lowercase q, but it can also be represented by change in enthalpy, or delta H, because remember, at constant pressure, delta H equals Q, and constant pressure is almost always a good assumption for the duration of an experiment, or at least as long as we stay at the surface of the Earth. For reasons that will become clear later, we'll use delta H to represent the heat change for this experiment. Specific heat capacity, represented by a lowercase s, is the amount of heat required to raise the temperature of one mass unit, like a gram or kilogram, of a substance by 1 degree Celsius. So it turns out that different amounts of heat create different temperature changes. Like metals get hot really easily and cool down really easily. Others, like water, require a lot of thermal energy to raise the temperature and therefore have to release a lot of heat to cool down. I'm always wondering though, like, what does that really mean? Like physically in the molecules, shouldn't heat raise the temperature of all substances equally? And why does water in particular have such a high specific heat capacity? Heat energy can do a lot of things besides just increase temperatures. Temperature, or the speed at which molecules bounce around, is just one way that atoms or molecules can absorb energy. Heat energy can also be absorbed by the breaking and formation of bonds between molecules. And as we'll learn in another episode, the extremely high specific heat capacity of water is due to the breaking and formation of hydrogen bonds that are associated with relatively small changes in temperature. And how do we know the specific heat capacity? Well, I am happy to report that some noble chemists have worked hard to determine the specific heat capacities of hundreds of substances so that we don't have to. We just have to look up the numbers in a table. Okay, so specific heat capacity times mass times the change in temperature. The mass is important because the more mass of a substance we have, the more chemical bonds are present. And because energy is contained in chemical bonds, they have a big effect on how much energy we're able to absorb or release. And finally, there's the change in temperature. When doing calorimetry, we calculate a change in heat by measuring a change in temperature. But as we've said a billion times before, heat and temperature are not the same thing. Please do not think that this thing is measuring heat, because it's not. It's just that luckily in this specific case, they are related by our handy little calorimeter formula. Now, you might not have noticed, but we are right at the interface between chemistry and physics here. Each science could claim ownership over these phenomena, but the truth is that humans made up the difference between chemistry and physics anyway. Thermodynamics, the study of heat, energy, and work, doesn't care about our little rules. Thermodynamics itself makes the rules of the universe. It is the ultimate law. So now you know, even though you might not have cared, what you should. Because it's cool. It's all wiggly wobbly, bondy wandy. All right, enough talk. Let's get out there, actually do some math here. Remember that the formula is delta H SM delta T. The solutions we're using here are so dilute that almost all of their mass consists of water. Therefore, we can simply use the specific heat capacity of water. If we look that up on a table, we'll see that it is 4.184 joule per gram degrees Celsius. I used 100 grams of each chemical for a total mass of 200 grams. And finally, we need the temperature change. If you remember, the temperature rose from 294 Kelvin to 301.4 Kelvin. The difference between these two is 7.4 Kelvin. It's a positive value because the temperature increased. Cancel all the appropriate units and then bang on the calculator to get a final release of 6,192.32 joules, or 6.2 kilojoules of heat from the reaction. Because this formula is based on temperature change, and since the temperature increased, we end up with a positive result. But most importantly, it tells us the magnitude of the change in heat energy. So I wonder how that compares to the amount we would predict you.
All right, so let's get back to our slide. So yeah, he was demonstrating that very simple calorimeter setup that we talked about, or you could have very more commercial setup with better insulation, more sturdier material, a built-in stirrer, a precision thermometer. A motorized stirrer will make sure that there's very rapid and even mixing of the solution, and the precision thermometer would give you a very good measurement of temperature. But really, the same thing can be done using a simple calorimeter made up of styrofoam cups, a thermometer, and just something to stir it with. So specific heat capacity is the amount of heat energy that is needed to raise the temperature of 1 gram of any substance by 1 degree. So specific heat capacities of various substances, for example, concrete, aluminum, wood, water in the liquid state, these are the specific heat capacities. And these are given in joules per gram degrees Celsius. So for concrete, it's 0.88. Aluminum, it's slightly higher, 0.9. For wood, it's 1.76. And for water, water has the highest heat capacity. Water has a very high heat capacity compared to the rest because, that's why it's used so commonly in calorimetry experiments. So in calorimetry, the total amount of the thermal energy that is absorbed or released by the chemical system is given the symbol Q, and its units are units of joules. And the value of Q, or the value of the total amount of thermal energy absorbed or released, is calculated using this equation. Q is equal to mc delta T. M is the mass of the substance. C is the specific heat capacity of the substance. And delta T is the change in the temperature of the substance. The final minus the initial gives you the change. Now, Q has 2 parts. It has the magnitude, which tells you how much energy was involved, and it has the sign, whether it's a positive value or a negative value, and that tells you the direction of energy transfer. If Q has a negative value, That means that the system transferred thermal energy to its surroundings and that the change was exothermic. Remember, the term exo means out. So thermal energy was transferred out to the surroundings, to the water, which is the surroundings in the calorimetry. That increases in temperature because it's receiving heat from the chemical reaction. If Q then has a positive value, that means then that the system absorbs thermal energy from its surroundings and that the change is endothermic. Endo means going in. So the water in the calorimeter decreases in temperature because energy is leaving the water and going into the chemical reaction. And these specific heat values of various substances are often available to us in tables, and we can look it up. And yeah, you can see that amongst all the substances listed, liquid water has the highest specific heat capacity. That means it takes the highest amount of energy to raise the temperature of 1 gram of it by 1 degree compared to all the other substances. Okay, so let's look at one example together. So suppose we see a question that we're wondering, when we have 500 milliliters of water in an electric kettle that is heated from 25 degrees Celsius, roughly room temperature, to 65 degrees Celsius, so quite hot, how much heat energy flows into the water? So first of all, we have to look at what we are given. So we write down what are we given. We are given the volume of water, which is 500 mils. The specific heat capacity of water, we can easily look up from our tables. And we can figure out the change in temperature. So the final temperature, which is 65 degrees, minus the initial temperature, 25 degrees, produces a change in temperature, a delta T, of 40 degrees Celsius. So those are things we know. And from that, we want to know the Q, how much heat energy. And we recall that our equation is Q is equal to MC delta T. So remembering, and I think this is something that most of you should know, and if you don't know, make a note of it now, that the density of water is 1 grams per milliliter. This is the density of water. And the density of water means how much mass for how much volume. So 1 gram per mil. So then we can use this relationship to understand that our 500 milliliters of water has a density of 1 grams per mil. That means that it weighs 500 grams. So we have 500 grams of water. And then we can use these values to calculate for Q. So once we put in our values for mass, specific heat, and delta T, and we multiply it out, and we see that the grams cancel out these grams, and the degrees Celsius down here cancels out the degrees Celsius up here, and then we are left with joules. So we have 83,600 joules, or 83.6 kilojoules. And then we finish it with a very clear statement, as we usually do in word problems, that 83.6 kilojoules of heat energy flows into an electric kettle when 500 milliliters of water is heated from 25 degrees to 65 degrees. Then there is some support questions for you guys to practice with. Which brings us to just more talk about the first law of thermodynamics, the law of conservation of energy. So if you recall, energy is always conserved. We can't create new energy, nor can we destroy energy by using it up. Energy can only be converted from one form into another. When any system undergoes any chemical or physical change, the change in the internal energy, the delta E, so the change in the internal energy, is the sum of the heat that is added to or liberated from, meaning taken away from the system, and this is Q, and the work done on or by the system, W. So delta E, the change in the internal energy, is equal to Q plus W, which is equal to the heat added or liberated and the work done on or by the system. This is an algebraic expression that describes the first law of thermodynamics. And here you have to remember the sign conventions for Q, W, and delta E. So when Q is positive, that means that the system gains heat. When W is positive, that means work is done on the system. And when delta E is positive, that means that there's a net gain of energy by the system. This all has to do with the system. But if the sign for Q is negative, then the system is losing heat. Then if the work is negative, that means the work is done by the system. And if the delta E is negative, that means that there is a net loss of energy by the system. So notice that the energy entering the system as heat or work has a positive sign, and that delta E involves not only heat, Q, added to or removed from the system, but also the work W that is being done by or on the system. And that delta E depends only on the initial and the final states of the system, not on how this change occurred. This means that although delta E is equal to Q plus W, does not depend on how the change occurred. The specific amount of heat and work produced depends on the way in which the change occurs. So for example, if we look at this diagram over here, if we have a battery and this battery is connected either to a thermal coil that's either giving off heat or giving off light, and the same battery is connected to a fan. So the delta E, the amount of energy lost by the battery, is the same in both cases. In one case, it is lost as heat when the battery is fully charged to the point where it is completely discharged. You've completely used up your battery. That change in energy was heat. In the case of the fan, when your battery is fully charged to the point where it becomes fully discharged, it's the same amount of heat being lost by the battery, the same amount of energy, being lost by the battery. It's just that in the case of the fan, it's being lost as some heat and some amount of work because the fan is spinning around and propelling around and doing mechanical work. But overall, it's the same amount. And that is the first law of thermodynamics, law of conservation of energy. And energy can't be created or destroyed. It can only be converted from one form. In this case, a chemical energy that is stored in the battery, to another form, heat energy, or to another form, some amount of heat and some amount of work, which overall adds up to be the same. Now, enthalpy or H. Every substance that undergoes a chemical or a physical change has a certain amount of thermal energy. The chemical and the physical changes that take place around us are happening underneath the constant pressure of the Earth's atmosphere. So like, as we heard in the video, unless you're leaving the Earth, it's a pretty good assumption to make that the changes that we are talking about are taking place under constant pressure. And when a change takes place under constant pressure, that change in enthalpy, which is referred to as delta H, equals the change in the internal energy, which was the delta E we discussed in the last slide, plus the product of the constant pressure, so P, times the change in volume, delta V. And since delta E is equal to Q plus W, then work is equal to minus P delta V, the work involved in the expansion or the compression of a gas at constant pressure. So then we substitute those into delta H, delta E plus, and we get this delta H is equal to delta E plus P delta V. And we substitute in further, and we get that Q is equal to Q plus W minus W, and delta H is equal to QP finally. And this subscript P on our QP, this P down here, indicates that the process is happening at constant pressure, the constant pressure of our Earth's atmosphere. Or perhaps we're doing doing this reaction under a pressurized closed system, but we're still maintaining a constant pressure. Now, because this QP is something that we can either measure or calculate, and because so many physical and chemical changes of interest to us are taking place at this constant pressure, enthalpy is a more useful function for most reactions than internal energy. So we tend to talk more about this change in enthalpy, delta H, than this internal energy of delta E. And also, most of these reactions, the difference between delta H and delta E is very small, because this P delta V is often a very small term. So therefore, this energy change that occurs in a system during a reaction called the enthalpy change, this delta H, can be measured using our calorimetry data, this QP value. So let's talk about molar enthalpies. Molar enthalpy change, which is denoted by this delta H subscript R of reactions for a substance. So this little R indicates that there is some sort of a reaction, and it's the molar enthalpy change reaction for a substance, is the energy change that occurs when 1 mole of that substance undergoes a physical or a chemical change. And that's why these are called molar enthalpies. So the symbol delta H, the R, indicates what type of chemical reaction, and the SI units is joules per mole, because this is molar enthalpies. It's how much joules per mole. And it's written as either joules per mole or kilojoules per mole. For example, we might have a reaction that produces water. We have hydrogen gas reacting with oxygen gas to produce water. And it produces 285 kilojoules. Or another way to say it, to write it down also, is this way. we can either put the kilojoules as a part of the reaction, because since it's producing this heat, or we can write it outside of the reaction on its right side as delta H, and make sure we give it a minus value because it's an exothermic. This was produced by the system. And that's another way of writing this, for example. So here, the delta H per mole of a substance in this reaction is minus 285 kilojoules per mole. And minus because it's being produced, because this is an exothermic reaction. So make sure you put in the minus. And here we have 1 mole of hydrogen reacting to release 285 kilojoules of thermal energy. So when we write a balanced equation for this molar enthalpy change of formation of a product, the coefficient of that product must always be 1. So if this was the molar enthalpy change for the formation of water, for example, we have to make sure that the coefficient here in front of water is 1, as it is in this case. And other substances in the equation might have fractional coefficients as a result. For example, oxygen here will have a half, the coefficient of a half. But if we are talking about this being the molar enthalpy change of formation of water vapor, then we have to make sure that the only coefficient in front of water here is 1. That is, it isn't 2 molecules of water, it isn't half a molecule of water, it isn't 6 molecules of water, it's for 1 molecule of water. And these are molar enthalpies of formation. So there can be molar enthalpy of formation, and there's other types of reactions. For example, solution. For example, when sodium bromide is going into solution and it's becoming aqueous sodium ions and aqueous bromine ions. It can be a combustion reaction. For example, the burning of methane with oxygen to produce carbon dioxide and water. It can be the vaporization of methanol from the liquid state to the gas state. It could be the formation of methanol, for example, the reaction of carbon plus hydrogen plus oxygen to produce methanol. It can be a neutralization reaction. For example, it can have 2 molecules of sodium hydroxide reacting with 1 molecule of sulfuric acid to neutralize, to give this sodium sulfate salt and water. And that will have 1 value. And that would be the neutralization of H2SO4. That value would be respect to 1 of H2SO4, or that could be the neutralization reaction for 1 molecule of NaOH, in which case the coefficient for NaOH will have to be 1. The coefficient for the sulfuric acid will become a half, and the coefficient here will also become a half, and then this becomes 1. So it all depends which one you're talking with respect to, as this table shows here. So just to summarize enthalpy, enthalpy, or H, is the total energy of a substance at a constant pressure. But delta H, the change in enthalpy that accompanies a chemical process, is referred to as delta H. And in chemistry, we study delta H. We study the change in enthalpy that accompanies some chemical process, some chemical reaction. And the delta H, the change in enthalpy of any process at constant pressure, is equal to its change in heat at that constant pressure. It's equal to Q. And so delta H can be associated with these physical changes, such as melting or vaporizing, as well as chemical reactions, such as chemicals reacting together, or a combustion reaction, neutralization reaction. And molar enthalpy change, this delta H R for a reaction, this R refers to the reaction. And then down here, instead of R, you will write what kind of reaction, like we had over here. Instead of R, you would write, okay, this is a solution, going into solution reaction, or a C for combustion, or a vape for vaporization, or a little F for formation, or neut for neutralization. You indicate what kind of a reaction. For molar enthalpy change of a reaction, you replace this R for what reaction is the change that occurs when 1 mole of that substance undergoes a physical or a chemical change. So for example, like we talked about in these, when 1 mole of this acid is neutralized, or when 1 mole of this base is neutralized. See, these reactions, although they are the same reactions, they're written differently with different coefficients, because it's either with respect to 1 mole of the acid or with respect to 1 mole of the base. Either 1 mole of the acid is getting neutralized or 1 mole of the base. So molar enthalpy changes of the reaction has to do with 1 mole of that substance undergoing that change, either physical or chemical. And what you have to then remember is exothermic reactions, the delta H's are having always a negative value. Or if otherwise, you can also write it on the product side of the equation with a plus sign. And in endothermic reactions, the delta H's are written as plus, or they're put on the reactant side of the reaction with a plus sign. Stating that the molar enthalpy is a method of describing the energy changes in a variety of physical and chemical changes involving 1 mole of a particular reactant or a product, just like we said before. For example, let's look at a vaporization reaction, which is actually a physical change, because water is going from liquid state to vapor state. So you can either write your, and this is an endothermic reaction that requires input of heat. So you can either write it this way with the 40.8 kilojoules on the reactant side. See, it's being used almost as a reactant because it's being put in to the reaction. Or you can write it over here on this side with a positive sign. You can write it as delta H vaporization, with a positive sign, because this is a endothermic reactions. And these are values that are actually obtained empirically by scientists doing experiments and measuring these values. For example, for sodium, you could have the molar enthalpy of fusion, or you could have molar enthalpy of vaporization, and they're different values. Same with chlorine, same with water, same with sodium chloride. Or you could have, for ammonia, you could have molar enthalpy of vaporization. So you just have to be very clear what values and what type of reaction this is for. And then you know also that for molar enthalpies, you have to make sure it's not just kilojoules, but kilojoules per mole is the unit. That's the other very important thing to remember. So now we just want to keep in mind that the quantity, the amount of energy involved in a change, the enthalpy change, the delta H expressed in kilojoules, depends on the quantity of matter that undergoes the change. So it's important to keep in mind that those two are related together. For example, it will take twice the amount of energy to convert 1 liter of liquid water to water vapor as it does for 500 mils of water. So of course, for 500 mils of water, it might take a certain amount of energy. For double that amount, for 1 liter, it's going to take double the amount of energy. So these are related. And to calculate the enthalpy of change, that delta H, for some amount of the substance other than 1 mole, you need to obtain the molar enthalpy value from a reference source and then use the formula, whatever coefficient it is, where N is the number of moles and delta HR is the molar enthalpy change for that reaction in joules per mole. And N, which was the moles, you can get that from, say, the mass and from the molar mass in grams per mole. Those are relationships which you should be familiar with. So let's look at an example to go through what we just talked about here. So to use a sample calculations of how we can use molar enthalpies to do heat calculations. For example, Freon 12. Freon 12 has a molar mass of 120.91 grams per mole. We just keep that in mind. That's something that's useful to know. Freon is a common refrigerant. It's used in the refrigerators and it vaporizes in the tubes inside the refrigerators and it releases its heat. This results in heat being released to the outside of the fridge and therefore cooling the inside of the fridge. So if you have, let's say, 500 grams of Freon vaporized, what would you expect the enthalpy of change would be of this vaporization? Okay, so given for Freon, we're given that the delta H of vaporization for Freon is 39.4 kilojoules per mole. Did we have Freon here? No, we don't, but okay, so that's something that we are given from a table. So this value is something that we are going to be given. The vaporization for 1 mole of Freon is 34.9 kilojoules per mole. Our molar mass for Freon is 120.91 grams per mole. That's another given that we are told. The mass of Freon, we are told that we have 500 grams of Freon, and we're asked to calculate the change in enthalpy, the delta H. So first, let's figure out how many moles of this Freon we have. First, let's calculate how many moles of Freon. We know that there's this relationship of number of moles is equal to mass divided by molar mass. Okay, so the grams and the grams cancel each other out, and the mole in the denominator then comes up here and becomes mole. So the units all work out. And we also have this energy of the delta H, the change in enthalpy is equal to the number of moles times the change in vaporization per mole, the molar energy of vaporization. So first, let's calculate the number of moles of Freon. So N is equal to mass divided by molar mass. So 500 grams of Freon divided by 120.91 grams per mole. Grams cancel each other out, mole flips up. We have 4.135 moles of Freon. So we know that much. Next, we want to calculate the enthalpy change. So now delta H is equal to 4.13 moles times 34.99 kilojoules per mole, because this 39.99 kilojoules was the amount for 1 mole, kilojoules per mole for 1 mole. But we don't have 1 mole. We have 500 grams of it, which is equal to 4.135 moles. So if you multiply it out, we see that for this many moles, the delta H is equal to 144.7 kilojoules. So then we write our expected statement that the expected enthalpy change when Freon 12 is vaporized, when 500 grams of Freon 12 is vaporized, is 144.7 kilojoules. Was everybody able to follow this example through? Any questions?
No.
Okay, great. So if there are any questions, let me know. Otherwise, we are going to move on to another example. So here we are doing this course virtually. We're not actually able to perform these calorimetry experiments, but we can practice how we would do the calculations should we have a calorimetry experiment in front of us. How are we going to use those values that we measure to get our data? So let's look at another example. So in this example, you have a calorimetry experiment where you're measuring 7.46 grams of potassium chloride. So that much potassium chloride, you take that and you dissolve it in 100 milliliters of water. And you measure the initial temperature of this water is 24.1 degrees Celsius. And as you dissolve it, you notice that the final temperature of the solution actually drops. It becomes 20 degrees Celsius. What is the molar enthalpy? By molar enthalpy, we mean how many kilojoules per mole, how many joules per mole. Every time you see this term molar enthalpy, you know that your final units have to work out to be joules per mole or kilojoules per mole. So let's look at what is our given. What do we know? Well, we know the mass of our potassium chloride. We know the mass of our water. And we know the mass of our water because we know the volume of our water. And we know that the density of water is 1 grams per milliliter. So 100 milliliters of water must be 100 grams. And we know the heat capacity of water. We know the molar mass of potassium chloride because we have, we know it's 1 potassium plus 1 chloride adds up to 74.6 grams per mole. We know our change in temperature. The temperature actually drops minus 4.1 degrees Celsius. That's the delta T. And what are we required to know? We are required to know what is the delta H of solubilization of potassium chloride. What is the molar enthalpy of the reaction of potassium chloride going into solution, right? We're putting potassium chloride into water. So this is delta H of solution. And these are the equations that are going to help us out. We know the relationship between number of moles, mass, and molar mass here. Mass and molar mass. So moles, grams, and grams per mole. We know that relationship. We also know this relationship. We know that delta H sol, or the molar enthalpy of solution, is equal to Q, which is MC delta T divided by N, the number of moles, because delta H sol is molar enthalpy. So we want enthalpy per mole. So we have to divide it by the number of moles that we have. And we also here want to recognize that the law of conservation of energy states that in this case, because pressure is constant, it always is whenever we are doing any type of reaction on Earth, P is constant, and work is equal to 0. Therefore, our delta H is equal to Q. Delta H is equal to Q, and that delta H of potassium chloride dissolving would give us the Q of the calorimeter water. And that's how we can make this relationship here. In other words, N times delta H sol is equal to MC delta T. So that relationship there. Now, since these are just things you have to keep in mind as we're doing this, you have to understand that energy can't be destroyed. The total thermal energy of the system and its surroundings is constant. So the Q of the system plus the Q of the surroundings is 0. In other words, Q of the system is equal to minus Q of the surroundings. And by system, we mean the reaction that's taking place. By surrounding, we mean the water in the calorimeter that's surrounding the reaction. That's the surrounding. And the water is what the temperature change that we're measuring. It's the temperature change of the water. So both Q's are equal quantities here, but with opposite signs. So let's start by calculating how many moles of this potassium chloride have we got. So the number of moles, N, of potassium chloride. So using the relationship mass divided by molar mass, we know that we have 7.46 grams divided by 74.6 grams per mole is equal to 0.1 moles. Now, first, we are going to calculate the Q of the surroundings, the Q of the water. And the Q of the water is, their equation is MC delta T. The M is 100 grams. Remember, we had 100 mils of water. That's 100 grams of water. The specific heat capacity of water and the change in temperature of water. So that is equal to minus 1.7 times 10 to the 3 joules. But remember, the Q of the system is equal to negative Q of the surroundings. So that means that this minus 1.7 kilojoules is equal to plus 1.7 kilojoules for the system. The minus for the surroundings is the plus for the systems. They're the same. Then we calculate the molar enthalpy for the system. Since we know this relationship of N times delta H sol, this molar enthalpy of solution, is equal to the Q of the system for the chemical reaction. The reaction, actually not a chemical, but a solution, the dissolution of KCl, we can rearrange it so that we are solving for delta H solution, for the molar enthalpy of solution. And molar enthalpy of solution, if we rearrange this, is the Q of the system divided by N, or 1.7 positive 1.7 times 10 to the 3 joules divided by 0.1 moles. And that gives us 1.7 times 10 to the 4 joules per mole. Then we write our statement, which is very important. The final molar enthalpy of the solution is 1.7 times 10 to the 4 joules per mole. Okay, was everybody able to follow that along? I know it's a lot. It's quite a lot to think of. And I'm very sure that once you guys look at this again at home and at your own quiet time when you're studying this, you might have questions. You probably will have questions. Feel free to email me with questions or talk to me before class or after class, or read further in your textbook until you do understand how to do these types of questions and understand this relationship of the Q of the system is equal to minus Q of the surroundings. And that will help you to make sure you end up with the right sign when you're doing molar enthalpies of reactions. There are a few support questions for you guys to practice with. There are some calorimetry type of questions that will help you test your understanding. So let's talk about these enthalpy changes that we talked about, these delta H's. How can we represent them when we're actually writing them down? So there's 4 ways that you can correctly represent enthalpy change. One is as a part of the thermochemical equation. For example, you can write it if you have, for example, methanol, this combustion reaction of methanol reacting with oxygen to give carbon dioxide and water vapor. This is an exothermic reaction. This produces heat. So you can write that enthalpy change within the equation. And because it's an exothermic reaction, it produces heat. This delta H becomes, can be written following a plus sign, can be written in the product side of the reaction because it's a product that's being produced. You can also just write your chemical equation and leave some space, and to the right side, write that the delta H value is equal to negative 726 kilojoules. This way, it's not part of the chemical reaction. You're writing it sort of on the side, and you're making sure that you are giving it a negative value here because this is a combustion reaction. Enthalpy change is exothermic, heat is being produced. The third way, you can say it as the molar enthalpy of a specific reaction. For example, here, this can be viewed as the molar enthalpy of combustion for 1 mole of methanol. So here, the coefficient in front of this methanol is 1. It can be different values for all the other ones, but the important thing is because you're talking about methanol, so it's delta H of combustion is equal to minus, again, because it's exothermic, 726 kilojoules per mole, because you're talking about molar enthalpy. And you say of what? Kilojoules per mole of methanol. And then we know you're talking specifically about the delta H combustion for 1 mole of methanol in this kind of a reaction. And the fourth way is by drawing a potential energy diagram. So we can go through each one of these ways of representing enthalpy change and make sure that we understand that all 4 are correct. They are just different ways of showing the change in enthalpy. So first, writing it as a part of the thermochemical equation and the energy change being part of the equation. So if a reaction, as we've talked about before, is exothermic, the energy is listed with the products on the product side of the equation. That's on the right side, so listed with the products. If the reaction is endothermic, that means energy is being put in, then it would be written on the reactant side, on the left side. This is the reactant side. In both cases, the sign for it would be positive. You don't ever say minus or minus on when you're writing it as a part of the thermochemical equation. So here in this reaction, in this example, you're asked to write a thermochemical equation, for the combustion of butane. So this is a combustion reaction. The molar enthalpy for the combustion of butane is minus 2,871 kilojoules per mole. So this is the molar enthalpy of combustion for butane. For 1 mole of butane, it's this much. So if you remember from our previous unit, unit 2, that when you have a complete combustion reaction, the products of that reaction are, what are they? They are carbon dioxide and water vapor. Actually, let me correct this. This should be water vapor. So we write out our balanced equation, and we note that the molar enthalpy is minus 2,871 kilojoules per 1 mole. And this reaction, when we write it out and we balance it out, we notice that this reaction, we have it for 2 moles of butane. So calculate your enthalpy for 2 moles. If we're going to write it as a part of this equation, we need to make sure that this value that we're going to be putting in here corresponds to 2 moles, not 1 mole. This value was per mole, 1 mole. So we want to multiply it by 2 to get 5,742 kilojoules. And then we can use this as a part of our equation. We can put it into our balanced equation. And since this is an exothermic reaction, the enthalpy is negative. It's an exothermic reaction. So the enthalpy must be listed on the product side, on the right side. So here we write our equation, just as we have it, our balanced equation. And let me just correct this also while we're here right now. And we write this value on the right side because it's a product, it's being produced by this reaction. It's an exothermic reaction. We write it on the product side. And we also doubled it, if you remember, because this is for 2 moles of methane, whereas that value is for 1 mole of methane. So was that clear to everybody? Any questions here with this one? So this is a thermochemical equation with the energy term written inside the equation as a part of the equation, okay? The second way you can write the thermochemical equation is by not writing that delta H value as a part of the equation, but writing it on the side using the delta H symbol. You can write the delta H value beside it on the right side. Again, remembering delta H is negative for exothermic reactions and positive for endothermic reactions. So here in this example, we have sulfur dioxide and oxygen react to form sulfur trioxide. The molar enthalpy for the combustion of sulfur dioxide is minus 98.9 kilojoules per mole. And you're being asked, what's the enthalpy change for this reaction? So we start off by writing the balanced equation for the reaction of sulfur dioxide and oxygen. This is a combustion reaction. Sulfur dioxide is reacting with oxygen to produce this sulfur trioxide. We balance it out. So 2 plus 1 equals 2. We make sure we've got 2 sulfurs. We've got 2, 4, 6 oxygens on this side, and 2 times 3, 6 oxygens on this side. Yes, everything is balanced out. Now this value is for a 1 mole of sulfur dioxide. Here, our balanced equation gives us 2 moles of sulfur dioxide. So we want to make sure we multiply it by 2 moles to obtain the delta H for this reaction, which is actually for 2 moles, 197.8 kilojoules. And then we go ahead and we write our enthalpy value with our balanced equation. We write down the balanced equation that we worked out. Right here, we put it down. And then we write down our delta H value beside it. We say delta H is equal to negative 197.8 kilojoules. Okay, and that's the delta H for this reaction, the enthalpy change for this reaction. Okay, so that's another way to write delta H. The third way, make sure, any questions about this slide? Borna, Judy, Sasan, we're all good?
Yeah.
Great.
Yes.
Okay. So now we talk about the third way to write down delta H. So you remember that molar enthalpy, the delta H subscript R, is the enthalpy change associated with 1 mole of a substance. I keep emphasizing that because it's important to keep that in mind. The standard molar enthalpy, by standard molar enthalpy, we put in this delta, this naught value here. So delta HR naught is the term referred to this little 0 up there, is the energy change associated with 1 mole of a substance at a certain pressure, at standard temperature and pressure. And that standard temperature is 100 kilopascals and 25 degrees Celsius. So that's what makes it standard. It's the delta HR naught, 100 kilopascals and 25 degrees Celsius. So for example, you might be asked to write an equation whose energy change, this should be whose energy change is the molar enthalpy of combustion of propanol. So they're asking you to write an equation that represents the combustion of propanol, but the molar enthalpy of the combustion of propanol. So you want to make sure that you write down the equation in a way that you have only 1 mole of propanol. And then if oxygen has to be 9/2, if carbon dioxide is 3, if water is 4, that's all fine. But because you want it to be the molar enthalpy for combustion of propanol, you want to make sure that your propanol is 1. The coefficient for propanol, you're only doing it with 1 mole. You have to make sure it's balanced in that way. And because you're asked about the combustion of propanol, you know, in a combustion reaction, you react with oxygen to produce carbon dioxide and water. So you go ahead and you look up this value, this combustion, and you write down, these are just other, this is just other molar enthalpies of reaction. But here in the solution to this example is you just write down that equation. This is the equation that corresponds to whose energy change, the change in energy for this equation corresponds to the molar enthalpy of combustion of propanol. There's propanol, 1 mole of it, and this is a combustion reaction. So this is the equation whose energy change is the molar enthalpy of combustion of propanol. Now, the fourth way is to show delta H in a potential energy diagram. And the potential energy diagram is one way, is another way, is the fourth way of communicating graphically in a diagram and a graph how energy is transferred. And in potential energy diagram, you have the potential energy on the vertical axis, on the y-axis, and you have the progress of the reaction on the horizontal or on the x-axis. And you have where the reactants, the energy of the reactants and the energy of the products. Now, if you're talking about an exothermic reaction, where heat is lost, the reactants start with more potential energy and a certain delta H is lost. It's an exothermic energy, and you get products. The products are now of lower potential energy. If it's an endothermic reaction, the reactants start out with a certain lower amount of potential energy, and through the absorption, the input of this delta H, the products have a higher potential energy. And this is just for this chemical system. Obviously, energy is neither created or destroyed, but within the system, the exothermic reaction or the endothermic reaction, it's this way. So let's talk about maybe two examples of one exothermic and one endothermic chemical change. For example, if you have magnesium, solid magnesium reacting with oxygen gas, that is a highly exothermic reaction. It produces a lot of heat. And you have the delta H not a formation of magnesium oxide. And that is a value of minus 601.6 kilojoules. So you can show this value on a potential energy diagram. So we start out with our reactants and we go to our products, okay? And our products are of a lower potential energy because this is an exothermic energy. And an endothermic energy, such as water, decomposing to hydrogen and oxygen, this would be the delta H naught decomposition of water. The delta H naught. The naught refers to standard temperature and pressure. And this is the delta H naught of decomposition of 1 mole of water into its components, hydrogen and oxygen. And that's the value for it. And because it's endothermic, the products end up with a higher potential energy. And because it's endothermic, the delta H is written with a positive sign, whereas when it's exothermic, is written with a negative sign. Okay. And then we end up with our key questions, which are due on Sunday. Okay, this is from last term. So our midterm coming up is going to be covering units 1 to 3. And let me just see. So I was aiming for our midterm to be on Friday, October 29th. And we were talking about 1 to 3, but then you were telling me that I think there's some of you are taking some courses in school, not just here at Academy of Excellence. So 1 to 3 doesn't work out. And I think some of you are also taking courses with the Academy, and some of those courses are also on Friday evening, ending at 6, correct? So then, and I'm guessing if your class finishes at 6, maybe you just need a little bit of time to decompress. And so I think we can maybe hold it from 6:30 p.m. to 8:30 p.m. And that's what I'm going for. I don't know, have any of you received the official email from the school about this date?
No, I haven't.
Not yet. Okay. So I have been in touch with them. I have recommended this date and time. So is this date and time then possible for everybody? Friday, October 29th from 6:30 to 8:30.
Yes, I can do that.
Yes. Okay. Borna, Judy?
Yeah,
Yeah, good.
Yes.
Okay, perfect. Shadissa is not here, but hopefully this is an okay time for her too. Okay, so that's when our midterm will come, and it will cover the 3 units. So unit 1, 2, and 3. So just to bring us up to date, so we did unit 9 today. On Wednesday, we'll do lesson 10. Both of these questions, key questions, are due Sunday, October the 24th. Okay, and then lesson 11 is an independent study unit. So you guys can do this over the course of next week if you wish. It's optional if you do it, and if you do hand it in the following Sunday, then I can that can go towards bonus marks of, you know, you can drop a lower mark at the end of the year. You can drop one of your lower marks. But if you choose not to hand it in, then that's fine. You don't have to do it. Just look at the material and study it on your own. And obviously I will take it up in our unit 3 review session as well. So then on the following Monday next week, I will cover lesson 12 and then on the Wednesday, before we do our midterm exam, I will do a unit 3 review, which will actually be a good opportunity for all sorts of questions having to do from all of the units 1, 2, and 3. And between Wednesday, where we do this unit review, any other questions you might have, I still might be able to help you through email. But I really urge you to try and prepare yourself for the coming Wednesday, October 27th. That is almost like a tutorial session or like a review session. I have marked some of your work and returned it to you into your shared with me folder. By then we should be able to take up any questions that you had. I always try, and whenever I'm marking these assignments back to you, to write comments on it so that you understand if you made a mistake, if you answered anything incorrectly, then what is the correct way to answer it. But if at any time you don't really see, or you can't read my writing, or you're not sure you understand why this is not the right way, we can always take that up together. And lots of times I've done that with students, and it's not a problem. It's what we need to do. So yeah, that was our lesson on thermodynamics. And yeah, Wednesday we'll do enthalpies of reaction, and finally we'll wrap up with chemical kinetics and some energy options. Okay. All right, guys. Any questions either from today's lesson or previous lesson? We still have another 15 minutes left on the clock. Is there anything that you want me to go back to and explain again? Anything here that?
I just wanted to make sure again. So
Yeah.
when's our next, like, any type of evaluation?
Okay, so the evaluations are ongoing. Every week on Sunday, you have one.
Yeah, like the key
sometimes two.
questions.
The key questions. The key questions are part of your mark. They make up a total of 40% of your final grade are this. And then you have your midterm test coming up. We said we're aiming for the midterm being on Friday, October 29th. And
So that's the next like kind of test that we have?
That would be the, yeah, that would be the 30% is the midterm. And then at the end of the course, we have a final exam, which is another 30%. So yeah, so the evaluation is happening sort of constantly every week as we have assignments due. These assignments are each worth 2.5% each, adding up to a total of 40% by the end of the course. And then of course, 30% from the midterm, 30% from a final, adding up to your total grade.
So no regular tests?
No regular tests. The assignments are kind of like weekly open
Important.
book,
Yeah.
weekly open book tests, right?
Right.
So go ahead and do those, turn them in, and then the midterm test that's coming up at the end of Unit 3, and then the final exam at the end of the course, okay? And any questions that you have, anything you want me to clarify, anything that you think I said that maybe I said it wrong. Sometimes I'm caught up in talking and I might not use the right term. If I've tripped up, if I've said something wrong, something was unclear, I've made a mistake, go ahead and take it up with me. We can clarify that. I try and make sure as I'm speaking and as I'm delivering the lesson that I'm always focused on using the right words, but sometimes I slip up and the wrong words come out that sometimes confuse students. And if that happens, please, by all means, let's clarify that and make sure that everything is clear. All right. If there's any more questions, anybody?
No question.
No questions from you, Sasan. Okay. Judy, you're good?
Yes, I'm good.
Okay. All right, then in that case, I think I can maybe end the meeting now. And you guys can take this extra 15 minutes of your slotted time to review the slides and the lesson. I'm gonna share the lesson with you, and I'm gonna send also the recording of the lesson. I'm gonna share that also. I'm gonna email that to you as soon as I end this meeting and Zoom sends me the link. I'll share the link with you. And yeah, you can work on the assignments and have the assignments for me by Sunday.
Okay.
All right,
Thank
then
you,
in that
Miss.
case, yeah, I can end the meeting. I think Borna, you and I can talk a little bit more at the end. Okay, thanks, Judy. Thanks, Sasan.
Thank you.
Thank you. Bye.
Good night.
Have a good night.
You
Goodbye.
too. Take care. Okay, everybody else is gone. It's just us. So what was happening with you? You were kind of absent for several lessons and you didn't end up getting any of the assignments in. I've become quite concerned, Borna.
Yeah, so for my lessons, it's just right when my courses started, I got a job and I couldn't, like, I put in the schedule based on my schedule, like not knowing that I was gonna take these courses. So
Oh no.
I had to change them,
Okay.
and I changed it now, so I'm not gonna get any shifts that interfere with my lessons.
Okay. So then I'm just letting you know that I know that there was a few classes you missed. I think 3, possibly 4, I think you've missed. Make sure, go ahead and listen to those material, the recordings that I've
Yeah, there's
shared with
recordings.
everybody.
Yeah.
Yeah, go ahead, listen to them. And if you have any questions, anything that you are not clear on,
I email you.
Email me. Yeah, email me. I'm happy to explain to you. If you like, we can talk before class. We can talk like this after class if there's things that you need help with or you think Just anything, whatever it takes to bring you up to speed in the class, okay? I really want to see all of my students do really well as they can, as much as I can help them. I'm here for them. So I'm here to help. Just ask.
Okay, thank you so
Okay.
much.
Okay, no problem. Okay. So I wish you best of luck, and I hope you wish you great success in your job. I hope it goes well. And so yeah, I look
Thank
forward to
you.
seeing you next class and for all the upcoming classes.
Yeah, so Wednesday, right?
Yes, Wednesday again. Mondays
Okay.
and Wednesdays, 6 to 8.
Okay, thank you.
Okay,
Good
fantastic.
night.
Thanks. Good night, Lorna.